Here's the hardware that I'm setting up. Here's a high-level diagram of the setup. On the left is the MCU and the cryptographic coprocessor connected by a wire. This is the black board connected to the smaller red board in the previous photo. The black board can talk over bidirectional WebSockets connection to a Node.js server running on a laptop. The Node.js server in turn can talk to the Ceramic network or a database or a storage system in addition to the blackboard. Focusing first on the ESP32 or blackboard. This is the code I wrote to be compiled on the ESP32 as an RPC framework accessible over WebSockets. This framework takes a hex string. The first character, 0 through 3, allows for 4 separate conditions, matching a public key to the one stored on the cryptographic coprocessor, obtaining the public key from a cryptographic coprocessor, signing a payload with the private key on the cryptographic coprocessor, or accepting a payload message and reporting it. All other hex strings will be rejected. The next 4 characters specify the curve, and all characters following are consumed based on the conditions of the first character. That is what it is, 0, 1, 2, or 3. Now on to the Node.js server sending and receiving packets over a WebSocket stream with the ESP32.
In the remote signer branch of the Blinky project, I see the test JWT remote signer folder, which contains several prototype TypeScript files to be transpiled to run with Node.js.
This is a simple duplex WebSocket stream that sends a string to the ESP32 with the write method, which is parsed and interpreted by the chain of if statements on the RPC on the ESP32. The on method back in the Node.js server listens for a response on the WebSocket stream and prints the data it receives to the console. This is an early experiment to try to embed WebSocket functionality in a function. The purpose of this will be apparent later with the EIP 2844 experiments. On to connecting this system with the Ceramic network. The Ceramic network requires that a signer follow the EIP 2844 interface. There are 2 RPCs to interact with from the Node.js server's perspective, one for the ESP32 and one for the Ceramic network. For now, only authentication and JSON web signatures will be considered. Ceramic currently offers 2 implementations of the EIP 2844 JSON RPC interface, one for the Bitcoin SecP 256K1 curve and another for the Edwards ED 25519 curve. Both of these implementations look nearly identical. They both export a class that contains a constructor with a locally generated cryptographic key pair. Generating a cryptographic key pair on a device, cryptographic coprocessor, that is remote to the Node.js server adds complexity. Musing was in this GitHub issue. The signer function needs to be implemented with a WebSocket connection, or better yet, in a network-agnostic way. Since a WebSocket stream is an instance of an event emitter in Node.js, here is some code from a blog post by Derp Turkey that embeds an event emitter and asynchronous function. Here is my best thinking of how this should fit together. I haven't mastered the embedding, and some data is not properly returned from the asynchronous functions, like P56 signer and the remote public key. You're welcome to skip this, but here's the big picture. This was an earlier sketch of the basic functions that a Ceramic signer allows for. More broadly, it should allow for the creation of a Ceramic tile document with a schema. In the future, I would like to implement what is appropriate for authorization. Perhaps verify credentials, ZCAP LD, Cacao, or UCANS. Just a note, ceramic is rapidly changing. I will likely need to add a data model.